Okay, great. So thanks for sticking around. Last paper in the session, I know. This is joint work with Charles Hodgson, who is my intern at Microsoft. He's just literally in the process of moving to Yale. So he's just got his assistant professor job there. It's great, but he also is driving a moving truck across the country. Okay, so he can't be here. So the talk I have today is to start thinking about models of consumer search. And like the question that I referenced earlier, I've always been interested in how people interact with platforms, how people find goods, and how platforms can influence what you eventually find. And so to think about how platforms can influence what you eventually find on a platform, you have to have some model that's convincing of the search process. And so our goal here is to introduce a tractable empirical framework for modeling consumer search with learning. And what do I mean by that? Well, the classic models of search, sequential search at least, are earn models. So I learned about them in statistics in undergrad, right? So you imagine that you have a person, and they're thinking about trying to buy goods. All the goods look identical to them ex ante, but they actually have different prices. They go, they sample these goods from an earn. They see the price, and they go, is that a good enough price? Yes, no. If it's good enough, they eventually take it and they stop. And so it essentially becomes an optimal stopping problem. But this is a poor description of many of the search problems that we think about when we think about online platforms, and actually more generally. So what are those problems? The first problem is that search options are differentiated. I actually like to think about this in terms of, rather than the example I've given you here, but in terms of choosing a kindergarten, because I've just had to choose a kindergarten for my kid. So Cambridge Public Schools offers you a bunch of public schools, and all of them are ex ante differentiated. I know something about these options, right? I can go and investigate them further by going on a school tour, so I can acquire additional information, which is costly. That's the search process. But even before I start the search process, even before I go and tour the school, I know that this school is located here, and this school has maybe slightly fewer people in every class, or maybe slightly more. Well, this is private or not private. And so even before I start search, I have some information at my disposal. And this is true on Airbnb as well. Even before I go and read a lot of detail about any Airbnb option, I already have a map. I have some pictures. I have a rating. I have a price. So I already know a lot of things before I even go further into the search process. OK, so it's not like drawing things out of an urn. It's like there are many different urns, and they're just sort of labeled. The second thing is that people learn through search. So here I've got a picture of a railroad track, because this is what happens when you click through on one of these options. I don't remember which one. You go and you look at the detailed pictures, and you're like, oh, I'm going to be right next to a railroad. That's not very attractive. OK, so now I've updated on this option. I know it's not as great an option as I thought. But I also update on many other options, right? So it's not just that I think this isn't a good Airbnb. It's that, oh, all the Airbnbs nearby, they're probably near the railroad track too. They're also not good options. OK, and so what's going on in this model, if you try to write this down as a formal model, is that I'm learning about, I'm searching, and then I'm learning about payoffs, and my updates on payoffs are correlated. OK. So what are we going to try and do in this paper? We're going to try and introduce a tractable model of spatial learning in which sampling one product updates beliefs about nearby products in attribute space. OK? Then we're going to show that in that model, something interesting arises which wouldn't arise in traditional models, which is that there's path dependence. So where you start influences where you end up, OK, because of the learning process. And because of path dependence, it's possible for platforms to manipulate you. So if they can get you to start in the right place, which they might do, for example, by ranking something at the top of a list, then they also might be able to get you to end where they want you to end. Okay, and so that's interesting and only a feature of this model. And then we're going to show, if I get time to it, that there's some evidence of spatial learning in camera search data. Okay, so this is an example. Again, notation. I'll just talk about it. Okay. We have an example where there are 3 products. Utility comes from quality minus price. Price is something that's observed. So just because price is observed already, these 3 options are differentiated. A is going to be the cheapest. B is going to be the middle guy. C is going to be the most expensive. Quality is something you can only see if you pay the search cost C. But people know that quality is generally increasing in price. So quality is drawn from some normal distribution, multivariate normal, where it's price times some parameter mu that's above 1. And there's some correlation matrix which has positive correlation. OK. What's the optimal search strategy? So it turns out that if the payoffs, if the quality, if that matrix there, the sigma matrix is independent, so there's no covariance terms, then when you sample one product, you don't update on the mean utility of the other products. And in that case, the optimal search strategy has a very simple solution. And it's characterized by Weitzman. So this Weitzman paper, 1979, is a very nice paper if you haven't seen it before. It says that if you have you start with product C. Why do you start with product C? Well, in our example, price is a signal of quality, and the coefficient on price is more than 1. So it actually pays to go for the highest priced products because you're going to get more than that paid off in quality. So you'd sample C first. If it's high enough, you stop. If it's not that great, which is this green region, you now sample product B. That's the next one along on your list. And if that isn't good enough, you go and you sample product C, and then you choose the best one so far. Okay, at every point in the process, if you get a high enough draw, you'll stop rather than taking another draw and paying another search cost. This is the picture with positive correlation. Okay, to get this picture is kind of a pain because you have to solve the model by backward induction. And we can only really do it because we have 3 products. But this is an exact characterization of the optimal search strategy for those parameters. And it turns out that if you get a really high draw for C, you stop. But actually, it has to be really high compared to the previous picture because there's positive correlation. So if you get a high draw for C, you say, well, maybe B is going to be really good as well. So you think, oh, well, maybe one more draw. I'll try B. OK, so there we get product B. And so that's a new feature. Actually, if I get something really low, so if product C turns out to be terrible, I skip B completely. Why do I skip B? Well, I say B is close to C in price space. Apparently, I've just learned that price and quality are not that correlated in this particular set of products. I'd rather try the really cheap one. So now I make a very different decision. I go all the way immediately to searching product A in the green region up at the top. And then things get even more complicated. You can see that we now get things that aren't nice geometric shapes anymore. It turns out to matter that the search process is pretty complicated. OK. So that's one force of the model, is that there's now path dependence. The fact that I started at C means that sometimes I go to B next, and sometimes I go to A next. Whereas in the independent model, the order of search is completely fixed. That's a feature of the Weitzman model. What you're going to search, the order you can say predetermined. They're going to start with C, they're going to go to B, then they go to A. Here you change your mind as you go through the process. The second thing we want to illustrate, a second force I want to illustrate in this model is that platforms can potentially manipulate where you end up. So here I have an example with 3 products where B is closer to C than A. That is to say, B is more informative about C than it is about product A. A and B are exactly giving you the prior utility. So you thought they would give you the blue line. And in fact, those little X marks that you see mean that they did give you the blue line. That is their payoff. But product B, on the other hand, is much worse than you would have expected in this particular example. And we're going to assume that the platform knows that. So they've got 3 products, A, B, and C. A and C conform to expectations, but B is much worse than you would have thought. Can the platform get you to buy product A? And the answer is yes, they can. And what they should do varies depending on the search cost. If the search costs are very low, nothing is going to get you to buy product A. Notice that product C is the best product. The consumer should buy product C. It gives the highest payoff. And so it doesn't really matter what they show you. If the search costs are very low, you'll search everything anyway, and you'll get to product C. If search costs are very high, they can basically dictate exactly what you're going to buy, because you're never going to bother to sample another option unless it's a truly terrible product. And so they can put A in front of you, and you'll buy A. And that works. And that's sort of intuitive. When we think of rankings being manipulated by platforms, we think they'll put the one that they want you to buy at the top of the list. But there's this intriguing possibility that arises in this model, which is that with medium search costs, the thing that they need to do is, in fact, put product B first. What does product B do here? Well, product B is at the top of your list, so you search it. You then think, my goodness, it looks like I should update on the utilities. And when I update on the utilities, it looks to me like product A is now better than product C in expectation. So I search product A next. And then I stop, because at that point, I haven't updated very much on product C from the favorable draw. And A looks better than C still. So I've now managed to get you to buy product A. And the way that I did that was not by putting product A at the top of your list, but by putting product B at the top of your list and inducing these beliefs that product C was a bad idea. So in other words, a way to think about this is like a decoy product strategy. I don't want you to buy this thing that is actually pretty good for you. So what do? I give you an example of this that's actually pretty bad for you. get you to learn that this seems to be predictive that this is a bad idea, and get you to go somewhere else in the space. Okay. Okay, so let me, I've got 8 minutes left. I'm going to take those 8 minutes to tell you a little bit about the actual formal modeling and then a little bit about the empirical evidence that this works. So the modeling is going to be the following. We're going to have a model in which there's a characteristic space, denoted capital X here. Utility is going to be some, utility for product J is going to depend on the predictable part of utility plus an idiosyncratic J or epsilon ij. The mx function is unknown and the epsilon is unknown. So at the time of search, I don't know what the payoff I'm going to get from products are. But over time, I can learn what this function is. There's some mapping from characteristics to payoffs that I can learn over time. We think this is basically the mechanism by which learning happens, right? So when I think about kindergartens, or when I think about Airbnbs, how do I update? I go to a kindergarten that has a low class size, and I go, wow, this is fantastic. Maybe I'll like other kindergartens with low class size. That is to say, I map from the information I learned about this one particular object in some high-dimensional space, kindergartens, Airbnbs, and I have a model, which is these things are all similar in a way that relates to class size or geography or proximity to railroads. And so that's the thing I'm learning about over time. I'm learning within this lower dimensional space, which is a characteristic space. That we're going to make our life easy. We're going to assume that this function is drawn from a Gaussian process. And what people are learning over time is both the mean, is basically the mean function. And they're updating according to the covariance function. The covariance function depends on the distance in some characteristic space. Okay. So that's the modeling idea. It's a pretty simple idea. I think it's kind of how you would probably think about this problem if you thought about it for a while. But I think it is kind of important in describing real-world search to think about it that way. I think one reason that people haven't written down these models is because they're a nightmare to solve, right? So you can't really get closed-form solutions, optimal solutions for this search problem. In fact, the best you're going to be able to do is do n-period look-ahead and do something that looks like backward induction. What we're going to do to get explicit characterizations is do one-period look-ahead. So we're going to consider people who are thinking about, do I want to stop now, or do I want to make one more search? And so what's going to happen for these kinds of consumers is that every time they make another search, they're going to learn some information, they're going to update, and then they're going to think about, well, do I want to make one more search or do I want to stop? In these kinds of models, the options are going to be scored by search indices zj, which give the expected utility after searching product j and then stopping. And the optimal algorithm is I should stop searching if the best next option I have to search is not as good as just taking what I have right now after accounting for the search costs. And so these ZJs have this particular form which we derive in the paper. What I want you to take away from the explicit characterization, two implications which we can then test with data. The first is the following. If I have a bad experience with a product, a consumer should jump away to a farther away part of the characteristic space, all else equal. So think about, I'm going to show you this for cameras in a second, thank you. And the characteristic space is going to be price and zoom. So price is a very important element when thinking about most products. And zoom is kind of one of the key things when you think about compact cameras, how much zoom it's going to have. And so one of the things people are going to think about in our model is, if I just encountered a problem that had a really high price, and a camera that had a really high price, and it was terrible, should I keep searching high-priced products, or should I go and start looking at cheap cameras instead? Okay. Notice that this is not an implication of a model without the kind of path dependence we have. So again, in a standard kind of Weitzman-esque kind of model, you don't do anything differently because you just had a bad experience with a high-priced product. You just keep searching in the same order that you were going to search before. And then the second implication is, as I said earlier, the platform can steer consumers away. But it's this first implication that I want to tell you about in the last amount of time I have. So the data we have is from ComScore. It's a sequence of URLs. So people are looking for cameras, and we see across websites where they go. This across website thing turns out to matter a lot with search data. If you look at just a person's experiences on one platform, you often miss a lot of their search behavior because they look for things in multiple places. We have 1,000 panelists roughly, and we see all the product pages they load. And we also see that there's a difference between what people tend to search and what people tend to eventually buy. The search length turns out to be on average about 6 clicks. So 5.6 clicks. So people do actually do a fair amount of search in this example. And what Bronnenberg, Kim, and Meller have shown in their work is that there's this kind of swirling in towards the final product. So people kind of start far away from the product they're going to eventually buy, and then they kind of get tighter and tighter and closer to it. And so they entitled their paper "Zooming in: something," which was a clever title. Okay, what are we going to show you instead? We're going to show you that that people actually not only do they get closer and closer to their product, they look like little optimizers, as you might imagine in an explore kind of framework. So their step sizes in characteristic space decline over time. So that's what I'm showing you there. The search percentile is on the x-axis. It's how far along your search journey you are, where 1 is the end of your journey and 0 is the beginning. How far are you at that point? And for both price and megapixels, which is the zoom characteristic, I'm showing you that over time, they tend to take smaller and smaller steps, okay? Which is consistent with I'm trying to explore the space at all because I don't really know what's going on at the beginning. But then I kind of know what's going on, and I start zooming in a little bit. I start taking smaller steps. The other thing we're going to do is try show you a test of this, this theory model I told you earlier, which is one prediction of our model is that when you have a bad experience, you jump far away to another part of the characteristic space. So how can we measure what a test that we'd like to do is say, when you have a bad product, what do? We want to say you do something differently. So the first thing we need is a measure of bad product. So our measure of a bad product is going to be, I'm going to look at the eventual purchase data. You search 10 things. I'm going to look at who chose what, and I'm going to run a straight load regression. So I'm going to try and predict what you chose after accounting for observables, so after accounting for the xj's, as a function of those characteristics and a latent term, Cj. A Cj here is going to mean a surprisingly good product, and a bad version of that is going to be a surprisingly bad product. This is something that was rarely chosen conditional on being searched, even after you conditional on observables. So I define bad products that way. And what I can then show you is that when you have a bad experience at period t-1, so this is the top row of this table, you tend to take steps away from it, further away from it in absolute value space. So if this is a very bad product is a very negative Cj, which means that the step sizes tend to be big. So it's the coefficient is negative, but it's negative times a negative, so it's positive. Right? You tend to step far away. And that turns out to be true of every characteristic we've looked at after controlling for many sorts of fixed effects. We have product fixed effects. We have density controls. We have, yeah, so it's as simple as you just looked at a really expensive camera. It was a real dud. You're now going to search either for a much more expensive camera or much less expensive camera. You're going to move away from this part of the search space. And what we can show is not only is that true, it's persistent. So this bad experience matters 2 steps later. So 2 steps away, if I look at your choices 2 steps away, you're again going to be further away. 3 steps away, you're going to still be further away. So people who had a bad experience are going to avoid this area in the future. And so that's basically, I'm out of time, so that's basically the results of the paper. So in conclusion, what we find is that we advance a model of search which accounts for learning, and then we develop a test of that theory, and we apply it to data, and it seems to bear out reasonably well. Thank you.